last time we were talking about a pretty profound connection here between the physics of the motion of a particle in a viscous fluid and the motion of an atom moving in a near-resonant laser field that of an appropriate intensity and detuning. So if we have a particle moving in a viscous fluid, then we know the physics there. What we observe is that we have a drag force, we have friction or drag on the motion of the particle, which will tend to slow it down. But in addition, the particle doesn't come to absolute rest, but has fluctuations about that mean velocity 0. And that those fluctuations are arising from the fact that this fluid is not really an absolute continuum, but made up of discrete particles. And in fact, the observation of Brownian motion of a particle in a fluid was one of the most important observations and explanation by Einstein for the atomistic molecular constituency of matter, back in the late 19th century and early 20th century. And so damping and diffusion are interrelated when that damping is coming from, at the microscopic level, the random interactions between the particle of interest and the corpuscular components of the fluid. Okay? Similarly, here we have a situation where we have this particle moving in the laser field, and we know that when appropriately tuned, we get absorption and emission of photons by this atom. And one of the important effects that we get damping, as we discussed from the mechanism that we call Doppler cooling. So the important configuration here that we discussed last time is that we are looking at a situation where, as considered as a two-level resonance, our light field is detuned to low resonance, such that if it is shifted, if the effective shift loose shifts this in the rest frame of the atom, it absorbs more. And thus, as we discussed last time, we have a force in this configuration which opposes the motion. We have a friction force. Because if the atom is moving with positive velocity, it feels a force that opposes its motion because it absorbs more strongly from this field than this. And if it moves with negative velocity, then this guy should get shifted into resonance, and then it absorbs more from this field than that. And so whatever direction it goes, at least in this 1D configuration, we get a force that opposes its velocity. And that gives us damping. But in the same way that we just discussed, fundamentally, that damping is arising from the random collisions, if you like, between the atoms and the photons, that in addition to damping, there is diffusion and Brownian motion. And so this configuration of fields and atomic motion in the field was dubbed optical molasses, its analogy to the viscous fluid description of a particle doing collisions. Okay? So to get at the limits of how much we can damp the motion and what if this, from the point of view of the classical fluid, we know that if this fluid is at some temperature T, then through these collisions, eventually the particle will equilibrate with the fluid and come to the temperature. And the way in which we can look at that is through a Langevin equation that we'll remind ourselves of in a moment. So we need to derive an expression for both the damping and diffusion in order to understand what the ultimate equilibrium temperature will be of this particle moving in optical molasses. So when in this case, we're looking at the scattering force that gives rise to the damping, which has this friction coefficient, which is derived from looking at the balance of these forces. And this is the expression that we derived last time. Just one note here. So if I look at this damping equation, right, this is the force, the change of momentum as a function of time, then we get a damping rate, which we call the cooling rate. And that damping rate is then related to the ratio, or it is equal to the ratio of the friction coefficient to the mass. And that cooling rate has as its characteristic time scale the recoil energy. And that's one thing we discussed earlier on, which is that the time scale over which the external degrees of freedom of the atom, the motion of the atom changes, was related to the recoil energy. You remember we had this separation of time scales which allowed us to treat the motion of the atom essentially classically, because under the assumption that the recoil energy is much smaller than the internal damping rate set by the line width, then we were able to make that separation of time scales. And we see that explicitly here. The cooling rate, the rate at which the momentum is damped, is related to the recoil energy. That's not surprising. Okay? Right. So to get at the limits of the cooling, what we did is we returned to the Langevin description of the equations of motion, which says that really this equation should be thought about as an average, ensemble average over many random collisions, if you like, between the laser photons and the atoms. Okay? And if we wanted to see the fluctuations, then in addition to this average damping force, we need to include the random forces associated that are analogous to these random collisions that occur in a viscous fluid. And so this is not a deterministic differential equation. This is what we call a stochastic differential equation, because we don't know what this force is at any time. We only know its statistical properties. And for example, we make some assumptions here based on that we would later have to justify from the microscopics, that this fluctuating force on average is 0, so that we get this equation, but that there are correlations due to the fact that you collide and then you collide another particle in your fluid or a photon in your optical molasses, and under the assumption of the so-called Markov approximation, that is to say that the correlation time is essentially negligible between compared to the time scale over which the atom's momentum changes, then we have a delta correlated force, that's to say correlated in time, with a strength that is what we call the diffusion, related to what we call the diffusion coefficient. And as we showed last time, that diffusion coefficient is just what you get from thinking about once the particle comes to rest, it will spatially diffuse, and its momentum will diffuse as well due to these random collisions. All right. So, based on these equations, we can look at the fluctuations here. Are given by the average of the square, because on average the momentum goes to 0. So the fluctuations are then going to be related to the average kinetic energy. So however big that spread in momentum is determines, in a kind of equilibrium Gaussian approximation, what the temperature will be. And by the equipartition theorem, that defines the temperature, 1/2 kT per degree of freedom. So we have the rate of change of this fluctuation in momentum is damped and heated. Heated due to these the randomness associated with the scattering force. And if we then look at once this system comes to equilibrium, which means it reaches steady state, we get an expression for what these fluctuations are. They are related to this ratio, or equal to this ratio, the diffusion coefficient over the cooling rate. And in equilibrium, that then is then just equal to 2m times 1/2 kT. And so this gives us an important relation, a fundamental relation, which is related to what's called the fluctuation dissipation theorem. The fluctuation dissipation theorem says that fluctuations in the momentum and damping of the momentum are not independent processes. They are arising from the same physical mechanism. This collision, the random collisions between the particle of interest and the molecules in the fluid, or the photons in the optical molasses. And so the damping rate and the diffusion rate are not unrelated to one another. It's a fundamental relation. All right, so in order to get at what the temperature will be in optical molasses, we need to know what the diffusion coefficient is. We have the damping rate, the cooling rate, here it is. We need to know what the diffusion coefficient is. So, to do that, what we did is we said, well, if I look at a scattering process of this sort, and it's the randomness associated with this scattering process that gives rise to the diffusion, that the change in the energy of the atom under a photon scattering. So if the atom scatters a photon, the change in the energy of the atom was equal to related to the Doppler shift, vis-a-vis the initial velocity of the atom. There is another Doppler shift that's associated with the emission. So this is the Doppler shift in absorption. This is the Doppler shift in emission. And then we showed that there, in addition, there is always twice the recoil. Okay? Now, What this says is that if I am in the atom, I absorb a photon, h bar k. If I start with some initial velocity, I'll pick up, some recoil in that direction, pushing me. But then, in addition, once I'm excited, I will emit. But my emission is in a random direction. So, whereas these guys will say be bluer, and these guys will be redder from the Doppler shift, these guys are at the frequency no shift. Relative to the Doppler shift. So, if the atom is moving counter to the laser beam, so that this is negative, it'll absorb a photon redder than its resonance energy. But on average, although some of them are bluer and some of them are redder, on average, the emission, that shift, is 0, as far as the Doppler shift is going. So as far as the Doppler shift is going, if I average over many collisions, which is what this diffusion coefficient is supposed to tell us about, this is 0 in emission. So the fundamental Doppler cooling mechanism is seen here. There is energy lost in emission, and then there's a certain amount of energy gained through the scattering, which is due to the recoil, the random recoils. And it's the balance between these that determines the equilibrium temperature. So, what we see from this little exercise here is the following. If I have in this particular direction, what I see here is that the rate of heating is equal to the scattering rate times, or I'm saying how much the energy increases due to the heating happens at a rate due to the scattering rate from this optical axis with a energy heating of 2e recoil per scatter. So this tells me that 2d, which is the heating rate, twice the diffusion coefficient, is equal to twice the recoil energy times the rate at which I scatter those photons. And in this case, I have two beams. We're ignoring the small modulation due to the standing wave, and that's equal to twice the scattering rate. And the scattering rate is given by the saturation parameter over 2 times gamma for S small compared to 1, which we assumed to begin with. All right, so now we can put it all together. Says what we have here is that the equilibrium temperature, due to the balance between damping and diffusion in this problem, is equal to m gamma cool divided by the diffusion coefficient. Okay, and so that's then equal to, let's see, did I lose a factor somewhere? There's something. over it, it's upside down. Oh, I see what I've done wrong. Yeah. What I've written down here, this is the friction coefficient, not the damping coefficient. There should be an M here. Okay, so now I can put it all together. The diffusion coefficient here is equal to recoil energy times S over 2 times 2, that's that, divided by, let me just look at my notes to see if I get all this stuff right. Oh, okay, sorry, no wonder. I missed that. I see the other factor I missed. So the diffusion coefficient is the rate at which the fluctuations increase. This should be over 2n. That's the convention of the diffusion coefficient. Okay. So now it makes more sense. So now the diffusion coefficient is equal to 4 times the mass times the scattering rate times the recoil energy divided by the mass times the saturation parameter E recoil over H bar, and then there's a factor of 1 over 4. The bottom line of this, screwing up all the algebra, but getting it right at the end, is the following. So this is the equilibrium temperature, and it's the minimum value is achieved when the detuning is detuned by a half a line width to the red, and that temperature is known as the Doppler temperature. And the Doppler temperature is the limit that you can get from this picture of optical molasses, and that temperature in energy units is given by half the line width.
So M disappeared.
Yeah, completely. It doesn't depend on that. It only depends on the line. Now, I should say there was one sleight of hand, maybe more than one, but one important one here. When I describe this process, I mean, I talked about this in terms of the motion along one direction. But of course, the amount of recoil into a particular direction depends on the fraction of the scattered light that is scattered into that direction, because I'm talking about recoil along 1D. Really, this picture only makes sense, and it's the configuration in which molasses is always produced, whereby I have a 3D optical molasses. So I assume I have counterpropagating beams along all 3 x, y, z directions. in which case this picture is true for the recoil that happens into any one direction once I've averaged over all possible directions into which the photon can be emitted. Okay? We still have equipartition. We still have 1/2 kT per degree of freedom. So the whole analysis is correct. But this diffusion coefficient that I wrote down only makes sense when I have 3D optical molasses. Otherwise, I have to do some kind of geometric factors and think about how much of the recoil is going to be in that particular direction. Okay. So, optical molasses in 3D, this is the three-dimensional temperature. How cold is this? Well, pretty darn cold. If I make the conversion between megahertz and Kelvin, then 1 megahertz of line width corresponds to, I think I screwed this up in some previous lecture, but I just recalculated it. It's about 24.5 microkelvin. Okay, so in sodium, which was the first atom to be cooled in optical molasses, neutral atom, the line width is about 10 megahertz. It's 9.8 megahertz. And the temperature, the Doppler temperature for sodium is about 240 microkelvin. For cesium, the line width is about 5.2 megahertz. And the Doppler temperature is about, it's not so different, it's about 100, I don't know, it's 140, 125 microkelvin. Rubidium is about the same, a little bit hotter. Okay, so that's a darn cold temperature. I mean, that is, if you think about the coldest temperatures, well, first of all, what's the temperature of interstellar space?
2.7.
What?
2.7.
I mean, it's in the Kelvin, right? So we're talking orders of magnitude colder than that. And the coldest temperature, how cold can you get, say, if you wanted to cool a solid state device in a dilution refrigerator? How cold could you get it? I mean, that's a pretty darn expensive piece of machinery that tremendously difficult to work and get to the coldest possible temperatures in a dilution refrigerator. How cold can you get there? A few microkelvin.
But that's now cooling with helium-3 or
That's right. And pumping and trying to extract as much of the entropy as possible. So this is an incredibly cold temperature. Now, there's a lot of interesting physics here. If we come back and think about this picture, this analogy. So in the description that we had about thinking about a particle moving in a viscous fluid and coming to equilibrium, the temperature that this particle reaches is given by the temperature of the bath. It's coming into equilibrium, thermal equilibrium between the bath, this fluid, and whatever initial temperature it had. And so the particle eventually, we know there's a second law, the entropy of this particle will increase. Or I shouldn't say entropy of the particle, the entropy of the system will increase. And the fluctuations that we see are related to the fluctuations in the bath. So what the heck is going on in optical molasses? Well, this really isn't exactly this problem. This is not black body radiation. This is not a thermal state of photons. This is some very pure quantum state of the light. Sometimes we call it a coherent state of the light. So, in that sense, this is not really just equilibrating with a bath at the same temperature. It's not exactly the same problem. So I ask you, how in the world, I mean, where's the entropy here? If this thing is coming to some thermal equilibrium, what's happened? In what sense is this? Does the second law apply?
So it feels like, I mean, well, let's see.
Well, yeah, you get. I saw some there.
Thinking about the scattering.
Exactly. I mean, there is entropy. The entropy is related to the momentum distribution. We're talking about motion here. So we start with photons that are all with fairly well-defined momentum distribution. And ultimately, we have lots of photons scattered all over the place. So there is, the second law is fine, entropy. But where are the fluctuations? How did we get from a situation, I mean, this system seemed to be, we might describe it by a pure quantum state. So why do we end up with something that we describe with temperature related to fluctuations? Well, in this case, what we're talking about are quantum fluctuations. Even though we have a state that we might describe as a pure quantum state of the light, that does not mean that every variable is defined perfectly. There is an uncertainty principle. And in particular, there will be fluctuations associated with the absorption. The number of photons this atom sees in a given time interval fluctuates. So the number of photons it interacts with, so to speak, on fluctuates. So there's fluctuations in absorption. In addition, there are vacuum fluctuations in all of the other modes, in addition to the laser modes that we're talking about. And it's those fluctuations which lead to spontaneous emission. Nonetheless, even though this system might be considered to be a pure quantum state, it still is describable, the description, from fundamental principles. And if you read the notes from Tanucci from Les Ouche in 1992, remember we discussed when we first started to talk about this, the interaction Hamiltonian. We said there was an interaction of the dipole with the laser field, but there was also an interaction of the dipole with the vacuum. And if we really were to treat all of this from first principle quantum mechanics, we would find that the equation of motion is exactly, at least to the degree to which the Markov approximation is a good approximation, which it sure is, that the equations of motion of the quantum mechanical momentum of the atom are the Langevin equations. And so it's an interesting thing, something I've never fully digested myself, is that we have a situation where really we don't have the same kind of thermal equilibrium of a system with a bath. But nonetheless, the quantum fluctuations in the system play the role of the fluctuations in the path. And once included, the description is exactly the problem of Brownian motion. And the connection between Brownian motion and laser cooling was, this was all the rage in the 1980s to really try to understand the fundamental description of optical molasses.
And the thing why I don't really understand the similarities is because in one case you don't have black-body radiation, but highly coherent.
This field is not, in some sense, at thermal equilibrium. I wouldn't describe the
It
light.
doesn't have this distribution.
It's not a black body distribution. And moreover, of course, it's distribution in energy and momentum. Here, this is light that has extremely narrow line width. It has very well-defined energy. And it also has a well-defined set of momenta, directions
The
of
thing
momentum.
that fluctuates here is, I think, the direction which the atom is scattering.
That's one important thing. There's another important thing is there's a fluctuation in terms of the number of photons.
Yeah.
So there's fluctuations in absorption, there's also fluctuations in emission. Both of those give rise to the fluctuations which determine a diffusion and a temperature. Okay, so now historically, optical molasses, well, the Doppler temperature and the Doppler cooling mechanism was first proposed by Henshin-Shallow and Wineland and Natano in the mid-70s, but it was achieved for cooling atoms in the mid-80s in Steve Chu's group. Now, what they wanted to do, once we had the problem with molasses is kind of nice, but in the same way we know Brownian motion, we have diffusion. So the atoms won't stick around for very long. They'll diffuse out of the molasses and go away. Moreover, as we discussed last time, the capture velocity range for molasses is not much bigger than the minimum temperature. In fact, in order to load atoms into molasses, the only way that it could be done efficiently was what we described at the beginning of our discussion, which is to take a beam of atoms and through either Zeeman slowing or chirp cooling, try to compress as much as possible the atoms coming out of the oven, and then load them into molasses, where they wouldn't stick around for very long. So, Chu's group, and it was based in the Bell Labs group of Art Ashton, who was one of the pioneers thinking about trapping of new particles. They really wanted to not only cool them, but trap them. Now, what does that mean? What that means is that we want a restoring force, not just a damping force, but a restoring force that pushes the atoms in position to whatever the equilibrium point is, while we're cooling them. So the first thing that was thought about was to think about radiation pressure traps. So for example, suppose I did the following. Let's imagine I have two laser beams that are diverging. Okay, so the focus of the traps are out here. Two different focus of the beams are out there. So if I'm an atom here, right in the center, I feel no force. If I'm an atom over here, the intensity is much higher, so the radiation pressure is big over from this beam, but small from this guy. And the same thing over here. That's all well and good. But what happens over here is that I get pushed out of the trap. And this is a fundamental problem if I think about the radiation pressure. Classically, we recall that this is proportional to the Poynting vector, right? So, if you look at this, what we see is that the divergence of this force field is proportional to the divergence of the Poynting vector.
Can't you just make it in 3D and have...
Well, let's explain why, no matter what. It's not going to work. This is why. No matter what I do, if my radiation pressure is proportional to the Poynting vector, it will not work, no matter what configuration of beams I use. You can see that because the divergence of this field, in order to have a trap, what you need to have is that the force pushes in all directions. It must have a non-zero divergence. The divergence must be negative at the center of the trap of this. If I think about this as a 3D force field. The divergence of this force field is what? From Poynting's theorem, it's related to the change in the energy density. I need to either have a sink or a source of energy. Otherwise, in free space, the photon will go somewhere else. So this is not zero. What this says then is that because I'm not absorbing or emitting right there, this is zero. This says that there is no trap from a radiation pressure trap if that is disproportional to the Poynting vector. And this was known as the optical Earnshaw theorem in relation to what you may remember from electrostatics. In electrostatics, I can't create a trap for a charged particle because that if I have no free charge to sink that, the divergence is zero. That is to say, the electrostatic potential satisfies Laplace's equation. And I always have a saddle. Wherever I might have a trap in one direction, but I'll always have an anti-trap in the other direction. And have a kind of saddle potential. The same thing is true for a radiation pressure trap if the radiation pressure is proportional, which it is classically, to the Poynting vector. Now, what people try to do, this is a little piece of history, they try to alternate, you have like this, and then you turn that off, and you keep kind of trying to alternate it. It kind of works, but there's a much better idea. And this was the insight of Jean Dalibard, the most brilliant guy you'll ever meet. Said, wait a minute. This is true classically. What about quantum mechanically? Is really this the case? Is the radiation pressure just proportional as a function of position? Is all of its position dependence just in the way in which the Poynting vector changes as a function of space? Well, let us remind ourselves what we discussed some lectures ago. When we said, so the scattering force, quantum mechanically, we said was related to the scattering rate for a given beam times h bar k, okay? That was our derivation here. And what we said is that if we looked at this as a two-level atom, and for weak saturation, then the scattering rate was this, which said that the scattering force here is proportional, and this maybe this intensity is varied as a function of position, like in this laser beam. And the scattering force then is proportional to all of its position dependence is in the intensity in the direction of the wave vector, which is proportional to this Poynting vector. So everyone back in the day was thinking we're sunk. Quantum mechanically, it looks just like we had classically. We can't make a radiation pressure trap. Maybe we can alternate the beams, do something, but we're not going to make a trap. However, this was true under this approximation. Our atoms are not two-level atoms. They always have multiple sublevels. They have to, if we're going to do, even in the most trivial description of my atom, if I'm going to have a dipole allowed transition, I have, say, an S to P transition. The S state, I might forget about spin and just think about it as having one level, but the P state is going to have multiple levels. So let's look at the transition S to P. We have different absorptions depending on the polarization of the light and whether it has sigma plus, sigma minus, or pi relative to the quantization axis. So the insight here is that by changing the way in which the atom absorbs as a function of position, make this saturation parameter a function of position. In a way that just doesn't just depend on the intensity, but also depends on the different oscillator strengths as a function of position, we can get away from the restrictions of optical aperture there. So what's the trick? The trick is to use a position-dependent Zeeman shift. How does that work?
Well, if you got a magnetic field that has a gradient,
Exactly.
have different levels at different positions.
That's exactly right. So let's say that we have a gradient in, so we're going to look at a situation where, let's look in 1D for a moment. Let's say that we have a field which near z equals 0 is proportional to, just write it this way. I want to keep my notation straight, so let me just, let's say. So what we remember, we have the Zeeman shift. The Zeeman shift is minus u dot b. And this is the G factor times the Bohr magneton times the magnetic field times the M value. Okay? In this case, we have, for this simple picture of an S to P transition, we have 3 different values of M. Okay? And let's let this magnetic field be a function of position. We call it the Z direction. So I'm going to assume that there is a region of space in which this varies linearly. I have a gradient, as was suggested in the magnetic field. So the magnetic field, as a function of position, you know, it does something here. It falls off eventually, but B as a function of Z. All right? So let's look at what this energy level diagram looks like as a function of position. Well, the S state is unshifted. The P state, the M equals 0 in this simple model is unshifted. But then we have the M equals plus, oh, I don't know why I wrote it this way. I always keep it in that order. Oh, what the heck? It's in my Hebrew note or something. So now we have the M equals plus 1 and 0, and the M equals minus 1. So what we want to do now is create a configuration such that if the atom moves, this is as a function of the z-axis, if the atom moves away from the z-axis, it gets, away from the origin, pardon me, if it moves away from the origin, in this case along the z-axis, it gets always pushed back to the origin. So what should we do? Well, what we want is that as, in the same way that we use the Doppler shift in the Doppler cooling, so that the atoms that moved with higher velocities felt a stronger radiation pressure, we want atoms that move away from the origin to see a higher radiation pressure that moves them back to the origin. So that we want to have red detuned light so that we have a damping force. And if we use red detuned light, we want it to be that the atoms that move out farther also see a stronger radiation pressure. So, if I detune to the red, this will be resonant with sigma minus light. And if I'm out here, this will be resonant with sigma plus light. Which means that I can create simultaneously a damping force in velocity and a restoring force in position through the following molasses configuration. Let's assume this is the z-axis. This is my magnetic field as a function of z. What I want is that when the atom moves to positive z, it gets pushed backwards. So I should make this sigma minus. That means if this is the z-axis, the thing is spinning around relative to the z-axis with the left-hand rule. Okay? And what I want is that if it moves in the other direction, then it'd be more resonant with the sigma plus light, which means we should push it back into the positive z direction. So it should be sigma plus. Note, this is constantly a confusion. This sigma plus and sigma minus are with respect to this quantization axis, not with respect to the local K vector. With respect to the local K vector, they're the same. Okay? It's not right hand versus left hand. It's sigma plus versus sigma minus relative to the quantization axis. Always a confusion. So this configuration gives rise to what we now call a Magneto-Optic or Magneto-Optical trap, or the famous MOT. A MOT is a configuration in which I get both damping due to the Doppler effect and restoring force due to the Zeeman effect. And in fact, we can create this in 3 dimensions. So, how do we do it? The way that this is typically done, first of all, I need to create this gradient magnetic field. As I say, I want a configuration where the magnetic field is 0 at the origin and then grows away from the origin. So to do that, one can create that by having 2 Helmholtz coils. Now, you know, if you have Helmholtz coils, then typically what you get is a uniform magnetic field, right? If you put the current in the same direction. But if you put the current in the opposite direction, this is the current in the coil, and you make them in the opposite directions, then you have 2 dipole fields which cancel one another right at the origin. And this is what's called a spherical quadrupole. Magnetic field. So the magnetic field looks like this. Best up to you on that. Okay? That clear, sort of? It's a quadrupole. So this field has a gradient, and in fact it's 0 at the origin, and it grows linearly away from the origin in all 3 directions. Of course, the gradient can't, the strength of this slope can't be the same in all 3 directions because del dot B is 0, right? So if this is a axial symmetric configuration, you know, del dot B here is zero, and if these guys are equal, then this thing has to be half as big, right, in order to keep del dot B equal to 0. Nonetheless, there is a linear gradient in all 3 directions. So what that means is I have this configuration. B is increasing in this direction. So I have sigma minus, sigma plus, the way we discussed. The gradient is increasing here. Let's see, did I draw this right? This is the positive guy, yes, so this is sigma minus, sigma plus. Now, this is a little bit confusing here. Because when I talk about sigma plus, if this is the z-axis, this is what I'm calling sigma plus, and this is what I'm calling sigma minus. Yes?
Directions opposite at the local kilometer, isn't it the right hand rule?
I'm sorry, I don't understand the question.
Sigma plus and sigma minus, don't we use the right hand rule to the local k vector?
No, we do not. So this was the point I was trying to emphasize here. Sigma plus and sigma minus do not denote the helicity of the light. The helicity of the light is as you defined. it is defined as the circularity relative to the local K vector. Sigma plus and sigma minus have to do with the rotation direction relative to a space-fixed axis. The atom doesn't know what direction the light is propagating as far as its internal degrees of freedom go. I mean, it does relative to the momentum recoil, but relative to its internal, so it sits here and sees, woo, it's going around this way, woo, it's going around that way. It doesn't know what direction it's propagating. So it has a particular angular momentum, and then all of a sudden it feels this photon spinning it around, and it's that direction relative to some quantization axis that we define. Okay? Now, what's a little bit odd about this picture, but it's a standard, is that there are different local quantization axes that we choose. The assumption is that, you know, there's a gradient along this direction. There's a local magnetic field that defines a local quantization axis. It's defined by the magnetic field. And locally, the magnetic field is strong in the z direction here and in the x direction here. So these sigma plus and sigma minuses for these different directions are defined with respect to different local directions of the magnetic field. Not the K vector, but the magnetic field. And then this is rotationally symmetric. So a MOT always has, I can't draw perspective very well, but the other guy comes in the same way. So this is, you know, sigma minus. Along the y-axis. And this generates a 3D Magneto-Optic trap. So the question is, what are the characteristics of this trap? So, along any direction, the force is the countering forces between the sigma plus and the sigma minus forces, which is the scattering rate times h bar k from each of these, where now, in addition to the Doppler shift, I have the Zeeman shift. Okay, so at the origin, this is what we had before, but now we have this additional shift in the frequency due to the Zeeman shift. And this is the scattering off of the sigma plus, which is this is the S0 to P plus 1 transition. And then we have the other guy. Sigma minus light. Delta is the opposite wave vector and the opposite Zeeman shift. So this is the scattering from the S0 to P minus 1 transition. So the detuning picks up plus or minus the Zeeman shift, depending on the end value. Okay? So in the same way that we expanded this for low velocities and got friction, we can expand this around the origin and get the restoring force associated with this trap. Yeah?
So the direction of the magnetic field changes.
Yes.
So we quantize direction along the magnetic. It's along the direction of magnetic field. If that will influence the result, the direction changes of magnetic field.
So there are important issues about if the atoms are moving in a spatially dependent magnetic field, will that tend to cause spin flips and change the internal degrees of freedom and thereby affect how the atom absorbs and emits. For the case that we're talking about, because at the end of the day, the atoms that we get are moving very slowly, the, how shall I say it? The spin of the atom, or the internal degree of freedom of the atom, adiabatically follows the magnetic field. So that, you know, it's moving along this direction, it's going to see shifts in its magnetic levels relative to this quantization axis. If it's moving along the z direction, everything adiabatically follows. It's really, otherwise the dynamics are very complicated. Yeah?
I don't understand something about this picture. So that picture over there with the S&P is fine for like, say you're going F equals 1 to 2, but what if you're going to like 2 to 3? And so you're going to use the closed cycling transition for sigma plus, but then how does it do the sigma minus transition for plus 2?
Okay. It doesn't do a closed transition.
Oh, okay.
So, we certainly haven't gotten there yet. So, I'll come back to this picture in a moment. Let me say a few words about, of course, this is not our atom. Our atom has electron spin, our atoms have nuclear spin. So we have many more magnetic sublevels and hyperfine levels as well, and fine structure levels. So,
Does it bump into the closed transition? Does it have to-
wait, hold on. Give us a moment here. So, so firstly, as Akash was intimating, we talked about earlier, when we thought about this as a simple Doppler transition, thinking about this as in terms of Doppler cooling, and thinking about this in terms of two-level atom, there was a particular transition we could choose. That was a cycling transition. We said there was, you know, the F equals I plus a half, M sub F equals I plus a half, where I is the nuclear spin. That's the maximum, that's the so-called stretch state. So for example, for sodium, that's where the nuclear spin is 3 halves. This is F equals 2, M equals 2. So this is in the S1 half ground state. And then we go to the maximum fine structure, the so-called D2 line. There is up here, there is the F equals, or F prime equals 3, M prime equals 3. And if we use just pure sigma plus light, then this is the only transition that's allowed if I'm near resonance, because I have to change M by +1. And even though there are, in fact, all these other levels around, this is the only one that's resonant. I'm about a half a line from resonance. Now, as you said, in fact, relative to this picture, right, we have the F equals 2, we have the F equals 1, we have the F equals 0 up there in the D2 line. So if I have sigma minus and I'm sitting here, well then I'm going to be resonant with this transition. And if I'm resonant with this transition, this is M equals 3, M equals 2, M equals 1. Try to draw this a little bit better. Then this is M equals 2, M equals 1. Well, then I can decay to all these transitions. This is F equals 1 in the ground state. Is that clear? Those are the selection rules, right? In fact, I can decay in addition to these guys. M equals 0. All of those are allowed because M can change by 1 and F can change. But actually, that's not true. No, I screwed it up. For these guys, I can, if I am resonant here, then I only go to those transitions because I can't go from 3 to 1. However, there's a little bit of off-resonant transition. This hyperfine splitting in the excited state is not infinite. So I'm detuned some amount from F equals 2, and I can still decay down into these other transitions because I have off-resonant scattering from F equals 2 in the excited state to F equals 1 in the ground state. Now, this hyperfine splitting is pretty big. So atoms that fall down here are SOL relative to photon scattering because they're just so far off resonance, we're not going to cool them, we're not going to trap them. And I'm quickly going to do, this is what's called optical pumping. So one of the effects of optical pumping that we'll talk about more next week, which pumps the things from one hyperfine state into another. So that's bad because I'll quickly just, after a few photon scatterings, I'll just lose some atoms, and we know we need 1 billion photons to cool us down, right? So this is bad. So what's always done in these kinds of situations is to put on what's called a repumper. So if I go, I repump, I don't know, you do it with pi light or sigma light, I don't know what it is, but if we just put on a resonant transition up to here. So let me get rid of all of this junk and start it again. So the problem is atoms that fall down here, if I make with pi light, in fact there's all these other levels as well, and to make that resonant, then I just quickly repump them back. They'll fall back down here where they have another chance to be cooled and trapped.
So we aren't actually in this MOTs game using the closed cycling transition. We're just
No.
Okay.
In fact, you bring up an important and subtle point, which is that in 3D optical molasses, there is no way for me to use a cycling transition. Why? Even without the MOT. Why can't I just have pure sigma plus in 3D optical molasses? Well, remember, let's just look at 2D optical molasses. Well, if I had 2D optical molasses, suppose I wanted to have pure pi light. Could I do it? Sure, I could do that, because I could make all of these guys, say, polarized out of the board, and call out of the board the z direction. Then I have pure pi light.
But with sigma plus, it's already impossible with 2 because they would have different
It's impossible.
directions.
I mean, even in 3D, I can't even have pure pi light, right? Because the third guy, the fact that I have to have the laser polarization transverse to the propagation direction, if I put a third beam into the board, it's going to have to be polarized in the plane of the board. So there's no way in 3D optical molasses my 2-level atom is appropriate description. Hint for next, why this whole thing falls apart. Our 2-level atom approximation is garbage. Okay, but what I wanted to say, just give you just a few few more words about this. So we do this expansion, and this force then, we have our damping coefficient and our Hooke's law. And this then tells me that I have a damped simple harmonic oscillator. Where this force is MA. And so I get a damped oscillator for this kind of thing. And so that you can ask what is the oscillation frequency, how does the oscillation frequency relate to the damping rate? And I'm not going to go through all the algebra here, but what you find here is that the ratio of the Doppler cooling damping coefficient to the trapping rate goes like the square root of the recoil energy divided by h bar times the Zeeman gradient over the laser wavelength. And it turns out for typical values, this is about 14 megahertz per centimeter for typical Mach coils. That's the Zeeman shift in frequency units over. And so what I found, looking at the literature here, is that this ratio of the damping rate to the oscillation in the trap is about 5 for sodium. So this is overdamped. Typically these traps are very overdamped. It's not like the atoms are rolling around in this trap. They're feeling much more friction than they are oscillation. So the magneto-optic trap, let me just conclude with just a few words, is the workhorse of all cold atom experiments. It was first demonstrated in 1987, and it's now, the standard thing that is used to collect and cool atoms for later further cooling and experiments. What one finds is that the typical densities is about 10 to the 10th to 10 to the 11th atoms per centimeter cubed. The volume of the trap is on the order of, a 0.5 millimeter cubed, typically, I guess. And we get about number of atoms is on the order of maybe 10 to the 7th atoms in the trap, about 10 million atoms in the trap. There's one other point about the MOT that I should mention, which is, so the first MOTs, I believe, were created using the method that we described with either chirp cooling or a Zeeman slower to try to compress as much as possible the velocity distribution coming out of the oven and then load that into the trap. That's rarely done, or if it's done in a few labs these days. But how in the world can we get around that? Because we described in the context of optical molasses, the capture velocity range was on the order of the Doppler temperature itself. They're not going to get very many atoms in that low velocity tail coming out of an oven. However, it turns out in this problem that because of this gradient in the magnetic field, there is something like the Zeeman slower going on right at the trap. Because the atoms that are hotter see a bigger Zeeman shift, therefore there's a bigger Doppler shift, which will make those higher velocity atoms resonant. So there is a kind of natural compression of velocities. It's not quite the same as, I don't think, as a Zeeman slower, but it's enough such that the capture range of velocities is over 10 times higher in a MOT compared to just pure molasses. And so in a typical experiment, what you do is you have a vapor cell, you have just some chunk of cesium or rubidium just comes out at the vapor pressure, and there's enough atoms in the capture range of the MOT that they'll just fall into this little region and get cooled and trapped and collected at this density with about this much atoms. One last point. What limits this density? Why can't I make them denser? Why can't I make the cloud denser, put more atoms together? What fundamentally limits that? Well, you might think collisions between the atoms do that. And in principle, that would eventually do something. Collisions, maybe they're good, maybe they're bad, but they'll do something. But well before that, because in this regime, when we're talking about temperatures of 100 microkelvin at these densities, we're not getting that much in the way of atom-atom collisions. They're just too far apart. So what's limiting that density? What limits that density is radiation pressure. You see, what we assumed here was each atom, and what we have in this ball of atoms here, when we described this force, we assumed each atom absorbed independently. But when I start getting too dense, then I can start getting multiple scattering. That is to say, the spontaneously emitted photon from one atom can be absorbed by another atom. And that will exert pressure that keeps the atoms apart. There's only so dense they can be when I'm detuned about a half a line width from resonance and I'm scattering, at 5 megahertz. So one of the challenges originally to try to get to evaporate the atoms so that we can get to a Bose-Einstein condensate was how do we get the atoms denser? And one of the first tricks that was played was a so-called dark spot MOT. A MOT where there was basically some part where the laser beam was blocked. So that if they were cold and just happened to fall into the dark, well then they'll just randomly stay there and they won't be feeding any more radiation pressure. And they're already cold, so we can just collect them more and more into that. And the dark spot MOT can get you to densities that are about an order of magnitude to 2 orders of magnitude bigger, about 10 to the 12. And that was an important starting point for being able to collide the atoms and evaporate them for BC. All right? Very good. All right, we'll pick it up next time and talk about why the fact that we made ourselves assume a 2-level atom was a really bad idea.